Episode 18, titled Law of Large Numbers, Stability, Variance, and Practical Implications, the goal is to learn why more data often reduces random surprises and to recognize the specific ways that can help or mislead you on the DataX exam. In analytics, many arguments boil down to whether an observed average is stable enough to trust, and the law of large numbers is one of the main reasons we expect stability to improve as we collect more observations. The exam does not want you to treat more data as a magic phrase, but it does want you to understand why averages tend to settle down and what kinds of problems more data cannot fix. This episode builds a clear mental model of convergence, variance reduction, and diminishing returns, then ties those ideas to monitoring, experiments, and evaluation. If you can explain how stability improves and also explain why design flaws still matter, you will avoid many distractors that rely on sloppy intuition. The goal is not just to know the law of large numbers, but to use it as a practical decision tool.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
The law of large numbers, often shortened as LLN after you have said law of large numbers the first time, can be defined as averages converging to the expected value as the sample size grows. In plain terms, if you repeatedly observe outcomes from a stable process, the sample average tends to move closer to the process's true long-run average as you collect more independent observations.
This is the reason we expect measured rates, means, and proportions to become less jumpy when we have more data. It is also the reason small samples can feel dramatic and persuasive, even when they are mostly noise, because random variation has not had time to cancel out. On the exam, you may be asked what happens to an estimate as you increase sample size, and the law of large numbers provides the core reasoning for why it becomes more stable and more representative of the underlying process. The important idea is that convergence is about the average, not about every individual value becoming predictable, and the exam expects you to keep that distinction clear.
Convergence is not the same as a guarantee about any single sample, and this is where many learners overstate what the law of large numbers gives them. The law describes what happens in the long run, but any one sample, even a large one, can still be unlucky or can still reflect unusual conditions. This matters because the exam may present a situation where a large sample produced an unexpected result, and the correct interpretation is not that the law of large numbers is wrong, but that randomness and real-world variation still exist. Convergence also depends on having observations that come from the same stable process, meaning the expected value you are converging to must actually be meaningful for the period and population you sampled. If the process changes over time, the true average can shift, and then your sample average can converge to something that is no longer relevant. DataX rewards the learner who sees convergence as a tendency, not a promise, and who remains cautious about making absolute claims from any single dataset. Variance reduction is the practical engine behind stability, and it explains why averages become less volatile as sample size grows steadily. Each additional observation adds information and also adds randomness, but the randomness tends to cancel out across many observations, leaving the signal more visible. This is why estimates like proportions and means fluctuate widely in small samples and settle down as you accumulate data, assuming independence and stable conditions. In exam scenarios, this often appears as monitoring metrics that are noisy day to day but stable month to month, because the longer window includes more observations. The key is that the variability of the average decreases as sample size increases, which makes the estimate more reliable for decision-making. This is also why confidence intervals often narrow as sample size increases, because the uncertainty about the average shrinks. DataX rewards this reasoning because it helps you choose correct answers about sampling, monitoring, and when more data improves confidence. A critical practical nuance is diminishing returns, because collecting more data improves stability, but it improves it slowly once you are already large. The idea that doubling the amount of data halves error is not generally correct for averages, because the reduction in random error tends to scale with the square root of sample size. This means that to cut random variability dramatically, you often need much more data than intuition suggests, and you cannot expect a small increase to produce a dramatic improvement. On the exam, you may see questions about whether collecting more data is worth it, and the best answer often depends on whether the current uncertainty is dominated by random noise or by design flaws like bias and confounding. Diminishing returns also means you should be strategic about where additional data is collected, because more of the same low-quality or biased data does not improve truth. DataX rewards the learner who recognizes that more data helps, but that the pace of improvement slows, and that you must consider cost and alternatives like better measurement. When you can articulate diminishing returns, your recommendations sound realistic rather than optimistic.
The law of large numbers is especially useful for monitoring metrics like fraud rate or uptime, where you want stability to detect real change.
A fraud rate is a proportion of transactions that are fraudulent, and if you measure it over a small window with few transactions, it can swing wildly just because of randomness.
Over larger windows, the rate tends to stabilize, which makes it easier to detect genuine increases or decreases in underlying risk.
Uptime metrics behave similarly because short windows can be dominated by a single outage, while longer windows reveal the typical reliability level. The exam may frame this as deciding whether a change is meaningful or whether it is noise, and law of large numbers thinking tells you that more observations reduce random fluctuations in the average.
This also supports setting alert thresholds for monitoring, because you can choose windows that balance responsiveness against stability.
DataX rewards using stability logic to design monitoring rather than reacting emotionally to short-term swings. When you apply the law of large numbers to monitoring, you are using it in one of its most practical forms.
However, biased sampling defeats the law of large numbers completely, because convergence to the wrong value is still wrong. If your sample is not representative of the population you care about, the average will converge, but it will converge to the expected value of the biased sampling process, not to the true population value you want. This is why selection bias, measurement bias, and survivorship bias are so dangerous, because they produce stable but misleading estimates. The exam often tests this by describing data collected from a subset, such as only active users, only successful transactions, or only devices that reported successfully, and then asking what concern applies. The correct answer is often that more data will not fix the bias, because the sampling process is flawed, and the fix is to correct the sampling or measurement design. DataX rewards this because it distinguishes mature reasoning from the naive belief that volume alone guarantees truth. When you remember that the law of large numbers stabilizes averages only when the design is sound, you avoid a common and costly misconception. This leads to a practical decision. When should you increase sample size versus improve measurement? And the exam expects you to make that distinction based on what is limiting confidence. If the primary issue is random variability in a well-designed sample, increasing sample size can reduce uncertainty and make decisions more reliable. If the primary issue is systematic error, such as missing data, inconsistent definitions, biased collection, or noisy measurement instruments, then improving measurement and design can deliver far larger gains than simply collecting more. The scenario often provides clues, such as inconsistent labeling, data pipeline gaps, or limited coverage of important segments, and those clues point toward measurement improvement rather than sheer volume. Increasing sample size can also be expensive, slow, or operationally constrained, so sometimes better measurement is the only realistic lever. DataX rewards answers that choose the lever that addresses the true limiting factor, because that is what a skilled analyst does under constraints. When you can articulate that you need either more independent observations or better measurement fidelity depending on the cause of uncertainty, you will choose more defensible answers. A and B tests, often spoken as and B tests, after you have said A-B tests in words, are another place where the law of large numbers matters because experiments need enough observations for averages to settle. In an A and B test, you compare outcomes between two variants, and each variant's measured average or rate is subject to random variation. With too few observations, the difference you observe can be dominated by noise, leading to false conclusions about which variant is better. The exam may frame this as deciding whether results are reliable, whether more data is needed, or how to interpret early fluctuations in experimental outcomes. Law of large numbers thinking tells you that as you collect more data, the measured outcomes tend to become more stable, improving your ability to detect real differences. This is closely tied to statistical power and confidence intervals, because stability of averages influences your ability to conclude that an effect is real. DataX rewards learners who know that premature conclusions from small experiments are risky, and that adequate observation counts are necessary for reliable inference. When you connect A and B testing to stability, you can choose answers that emphasize disciplined decision-making rather than impatient interpretation. Big data does not fix confounding or leakage issues, and the exam expects you to avoid assuming that scale automatically produces validity. Confounding can create relationships that look strong in large datasets but are still misleading, because the association is driven by a third variable or by selection effects rather than by a meaningful relationship. Leakage can produce near-perfect evaluation metrics regardless of sample size, because the model is inadvertently seeing the answer in the features or in the evaluation design. In both cases, collecting more data can actually make you more confident in the wrong conclusion, because the estimates become stable around a flawed inference. The exam often uses this as a trap by describing extremely strong performance or highly significant results and then asking what concern applies. The correct reasoning is that validity depends on design, independence, correct partitioning, and appropriate controls, not on volume alone. DataX rewards this because it reinforces that data integrity and evaluation integrity are non-negotiable foundations. When you treat volume as helpful but not curative, you avoid a major class of wrong answers.
The law of large numbers also ties to the stability of training and evaluation metrics, which is a practical modeling implication that the exam may test indirectly.
With small datasets, training results and evaluation results can vary widely from one split to another, making it hard to tell whether a model is genuinely good or just lucky. As dataset size grows, evaluation metrics tend to stabilize because each split contains enough data to represent the underlying process more consistently. This is why repeated validation and cross-validation become important when data is limited, because you need multiple views to estimate performance reliably. The exam may describe inconsistent evaluation outcomes across runs, and the best answer often involves recognizing that small sample variability is driving instability, and that more data or more robust evaluation can help. Stability does not guarantee correctness, but it improves repeatability, which is crucial for governance and trust. DataX rewards the learner who understands that stable metrics are easier to manage and communicate, and that instability signals uncertainty rather than incompetence.
Rare events require very large samples to appear reliably, which is a law of large numbers implication that matters a lot in fraud, safety, and anomaly detection contexts. If an event happens once in many thousands of cases, a small sample may contain 0 occurrences, creating the illusion that the event does not exist or that the system is safer than it is. Even moderately sized samples can produce highly variable rates for rare events because the counts are small and a few events change the estimate dramatically. The exam may describe rare outcomes and ask why metrics are unstable or what is needed to measure them reliably. And the correct answer often involves larger observation counts, longer windows, or targeted sampling that still respects evaluation integrity. This also affects model training because rare positives create class imbalance and can make evaluation metrics misleading if not handled carefully. DataX rewards recognizing that rarity changes sampling requirements because it prevents overconfident conclusions drawn from insufficient exposure. When you see rare but costly, your instinct should be that stability requires a lot of data or careful design. A useful anchor for this episode is that more data stabilizes averages, not broken design, because it captures both the power and the limitation of the law of large numbers. More independent observations reduce random variation in averages, making estimates less jumpy and more reliable for decisions. But if the sampling is biased, the measurement is flawed, or the evaluation is contaminated, the stabilized average can be consistently wrong, which is worse than being uncertain because it looks trustworthy. This anchor keeps you from defaulting to collect more as the answer to every scenario, and it helps you identify when the correct fix is to improve design, definitions, or data integrity. Under exam pressure, it also gives you a quick way to justify why volume is not the solution in certain contexts. DataX rewards this kind of balanced thinking because it matches how experienced practitioners handle uncertainty. When you can say that stability improves with more data only when the underlying process and measurement are sound, you are reasoning correctly. To conclude episode 18, choose one metric and then state how the law of large numbers helps, because that forces you to connect the theorem to a real decision context. Pick a metric like fraud rate, uptime, conversion rate, or average resolution time, and describe how small sample windows can produce noisy estimates that swing due to randomness. Then explain that as you collect more independent observations, the average tends to converge toward the true long-run value, reducing random surprises and making it easier to detect genuine change. Add the professional caution that this stability assumes representative sampling and reliable measurement, and that bias, confounding, and leakage can still produce stable but misleading conclusions. Finally, tie it to action by stating whether you would increase observation counts, lengthen the monitoring window, or improve measurement design depending on what the scenario suggests is limiting reliability. If you can do that clearly, you will handle DataX questions about stability, variance, and practical sampling implications with confident, exam-ready judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.